Uh, Thank you very much, first for the invitation. It's always a pleasure to be here, and in this occasion especially, to celebrate my friend Alfredo.
Thank you very much for that.
It's because of him that I've been coming to Brazil regularly. I don't know, this is probably the sixth time I've come, possibly. So the topic I would like to speak today, it's part of some work we have been doing for a while already. But recently with my colleagues Marcos Carcini, Mark Schroeder, and Nicolas Stier-Moses, we went back to a very basic question about these atomic, or rather non-atomic games, congestion games. So it was the question about what is the real meaning when you're doing this continuous time approximation. So just as a motivation, look, I want you to fix your ideas on this very common, precise situation that we all have some intuition about. So let's say you're planning for tomorrow. What are you going to do to come to IMPA? Which route you will take? And you have more or less an idea of when are you leaving, maybe at 8, maybe at 7:50, but not very precise. And of course, you don't know who you will find on the road. Probably many people, but you don't know how many, you don't know who exactly you will encounter. So the usual approach in congestion games is to think of this as a large game where you have thousands of players, and every player accounts for very tiny impact on congestion. And then you forget about the game and you go immediately to the continuous model. And this was in fact a precursor, let's say, of Nash equilibrium. It was proposed by traffic engineers, namely Wardrop and then many other people. And they formulated directly the model in terms of continuous variables. Flows were continuous, loads were continuous, travel times were continuous, and so on and so forth. So formally, a congestion game is trying to model strategic situations, games, conflicts between many players, and in situations that involve crowding externality, namely the cost or the benefit that every participant in the game gets. It only depends on let's say, on the number of players that are using the same strategy. So you don't care about the identities, you only care about the number of players. And I will mainly focus on the negative externalities, namely, the more players, the higher the cost. But in fact, congestion games, they work exactly the same in the other direction. For instance, in cost-sharing games, it may be worth for the players. Maybe the players are happy to be many because the cost will be just split among all of them. So your individual cost will go down. But for this, and all I'm saying here is valid not only for negative externalities, but also for congestion games where you have positive externalities. But to fix the idea, let's skip to the simplest case, where it's congestion in routing games. Okay? So as I told you, the standard approach is that you look at this as a game involving many small players, and then you model this as a non-atomic game, which means simply that you don't care about discrete structure. You don't count the number of players, but you just treat everything as continuous variables, flows. And the basic question, we went back, and I will tell you at the end why did we come back to this question, is in which sense is the continuous model close to the discrete model? It's intuitive, it's clear, but then you go on the literature and you find very, very little results on that. And maybe there is a reason for that. And what I'm going to tell you during this talk is two approaches on how to interpret small players. And there are probably many others. So I don't claim that the results here give an explanation. It just opens a question mark about what does it mean to be a small player. And I will focus on these two situations. A small player can be interpreted in the classical way that Wardrop introduced the model, by the way, in the 50s. A small player was a player that accounted for a small weight. Let's say a car is just an infinitesimal particle in a continuous flow. So you think of a player as a very small unit whose impact on congestion is negligible. So all the players are there. If you take Santiago, for instance, in the peak morning hour, it's about 500,000 trips. So you think of a game with 500,000 players. Each one of those is very small. And that's one thing, and that's OK. But there is a different way of thinking of a small player, and it's the second one. You have lots of players. Each player may be small but not negligible. A car, after all, a car has 4 meters long. It might be small, but it's not zero. But what might be zero is the probability that Alfredo and I go on the road exactly at the same time, and that we interact with each other. Because when I go out in Santiago, even if there are 500,000 trips going on somewhere, I'm not interacting with 500,000 players. I'm interacting with a small fraction, namely those whose departure time interferes with mine. Okay? And I will show you that in both cases, you end up, when you take both limits, you will end up in a non-atomic game, as the original Wardrop model, but they're very different in nature. And I will try to explain you how they look these two cases. So let me go. The first part will be on this convergence and of different types of convergence, different type of limits of large games, large congestion games. And the second part, I will talk about the price of anarchy. In fact, it was the other way around. We started discussing the price of anarchy. Eventually, we came back to this more fundamental question: what are we talking about when we do this continuous approximation? So, from a very, just to fix the notations, what is a congestion game is given by basically 3 elements. The first element is a set of resources. Maybe I can go here for an example. Let's say a routing game. The resources are the links. You look at your network, you have different links. You want to form a route. This will be your strategy. So you have a set of resources, in this case, the links. Each resource comes with its own cost. And the cost, in fact, is a function which takes the load of the resource and sets it to a value. Let's say the volume of drivers on that link, and depending on that load, it gives you the travel time that you will experience. That's the part of resources. Then you have types. You have players, and each player comes with a type. A type in the routing game is simply, what is your origin, what is your destination? That's your type, from where to where you want to go. And each type comes with a certain strategy set, which is just some feasible subsets of resources. For instance, if in a routing game, are just the paths. You're choosing a path. A path is a set of links. So you're using a set of resources. And the cost that you will pay is the sum over all resources you are using, which themselves depend on the load of those resources. And the picture is completed by these demands. So for every type, you have a certain amount of demand. Let's say the total number of travelers that want to go on this origin-destination pair. That's a congestion game. Now, there are several flavors of congestion games, depending on how demands look like. So in the non-atomic case, you're thinking of continuous flow, so many players with very small. So you treat that, all the demands and loads and the model, you describe it by continuous variables. Let's say fine-grained, not only many players, infinitely many players, I should say. And this is usually employed as a model for traffic. That's one case. And then there are 3 types of atomic games. In the atomic games, you go back to the more standard case of games where you have finitely many players. And then depending on what the player is allowed to do, you distinguish the model. So in the splittable case, you have a small or medium number of players. Each player has controls a certain amount of the demand, but the player is allowed to split the demand over different paths. So he can act strategically by splitting the flow. Let's say I have 3 units of flow to route. I can route 50% this time in this direction, so I can split my demand. So think of, we're still working with continuous models. I can split continuously, in any way I like. But now we have few players or medium number of players, and let's say that you're routing fluids or sand or packets in a telecom network, so that you can split your demand. The unsplittable case is on the contrary, where you have a finite number of players. Each player has a given demand to be routed, but he's not allowed to split it. So you're sending, vessels, airplanes. You cannot split the airplane halfway, send it one way and the other way. You just have to choose one route and stick to that. And then the random case is where, the demands are random. And there are many models that you can think of. I will just focus on one type of randomness. So what is a non-atomic congestion game? I recall the formal definition, because in the end I will prove that everything converges to this type of animals. So a non-atomic congestion game is characterized by continuous and perfectly divisible aggregate demands for each type. And in this case, you assume that every infinitesimal particle is a player, so you have infinite players. There is a continuum of players. Each one has a negligible impact on congestion, but congestion is built up by the aggregate effect of many players. And then how do you find a Wardrop equilibrium? It's very simple. You say, okay, the demand for each type T, let's say for this origin destination, somehow will split among all the strategies, let's say over all routes. So you have to split the demand over the different routes into non-negative strategy loads in such a way that only the optimal strategies are used. And that's written like this. You fix an origin destination or a type. You look at 2 different strategies, and you say, if anyone is using strategy S, it should be the case that the cost of that strategy is better than the cost of any alternative strategy S prime. Again, if I'm using route S, if anyone is using, if some positive fraction of the people are using that route, it should be optimal. And what is the cost of that? Well, the cost of the strategy is just the sum of the cost of the resources that are used, which depend on VE, which is the cumulative flow or cumulative resource load, which are obtained by just adding up all the flows or all the strategy loads which go for every possible type and on every strategy that uses that particular resource. Okay? That's the standard model. This is Wardrop equilibrium, introduced by Wardrop in 1950, just a couple of years before Nash. It's a continuous model. What about the atomic splittable? In the atomic splittable, it's very similar. Again, the demands are continuous, except that now you have, as I told you, finitely many players. Each one controls a fraction of the demand and uses, acts strategically. The splitting is done in such a way as to minimize the self cost. And I will not go into the details for this, this game, but I just mentioned that this is probably the only result which everybody will tell you. If you ask anyone in the field, transportation scientists or anyone, you say, is it true that the finite games converge to the non-atomic game? They say, yes. That was proven by Henri Marcotte in '85. And if you go to that paper, in fact, the only thing they prove is that the splittable games, in fact, have this property, which is here. If I increase the number of players, splittable, and the demand controlled by each of them becomes smaller and smaller, then in the limit you get exactly Wardrop model. And I'm a very close friend of Patrice, so I asked him, is there anything else that has come up after your work? Because you see, 85, it's quite a long time ago. And he told me, no, I'm not aware. That's the only thing I know. In fact, I was able to find some small cases beyond the splittable case. But, OK, maybe we can postpone that when we have more. So what I'm really interested here is the unsplittable case in both versions, the random and non-random cases, the unsplittable and the random demands. So how does it look, the weighted game? A weighted atomic congestion game, we have finitely many players. Each player comes with a type, an origin destination, say. Each player also comes with a weight. They might be equal or different. You may have cars and bicycles and trucks and you go. Every player has a size. And it must be assigned to a certain strategy. Every player has to choose a strategy according to his type. Every player chooses one route. It's not allowed to split. I choose a route, and my all weight WI goes to that route. So let me introduce some notation. I will denote XIE, just the indicator of the fact that player I is using the resource E. Okay? So it's choosing a strategy as I, which contains the resource. And then the load of the resource is just the sum over all players of the weight of the player multiplied by the indicator whether he's using or not that resource. And I should say that when all the weights are equal, this is the model of Rosenthal. In the 70s, he introduced a game, which is a potential game. It's a very well-studied model. I'm departing a little bit from that because I'm considering weights which are not homogeneous. So in that case, in potential games, in Rosenthal's case, you have equilibrium pure strategies. It is no longer the case where you have heterogeneous players. When weights are different, you can only hope to have equilibrium and mixed strategies, as any finite game. After all, this is a finite game. And then if a player randomizes, so delta of STI is just the discrete probability measures or the simplex over the set of pure strategies, over the routes. So every player randomizes the route that we'll take. And this will be denoted by pi I. This is the strategy or mixed strategy by player I. Well, as soon as I randomize, if player I randomizes, this XIE becomes a random variable. It's a Bernoulli with some probability. The probability of using that resource is just the sum of the probabilities of choosing a strategy which goes through that link. And then these loads are also random variables. So the nature of the game looks very different from wardrobe equilibrium. In wardrobe, we have continuous variables, no randomness, and now we're dealing with random variables. So maybe that explains why not much was known. Nobody really made clear how these things connect. And then, well, before we go to this connection, let me just recall what is a Nash equilibrium. This is the standard notion. So every player is choosing a mixed strategy, and we're at equilibrium if, when I fix a player I and I look any strategy which is played with positive probability, so if I'm player I and I'm willing to take strategy S with positive probability, it should be the case that the expected value of that strategy is better than any other strategy S prime. So it looks pretty similar. Just a small detail is that when I compute the value of a strategy, or the cost for me of a strategy, I will sum the cost over all edges of the loads. These loads VE are random, as I told you. In fact, these expectations with respect to the laws of these random variables. But I'm conditioning on the fact that I will go there. So I compute what is the expected value of that road, conditional on the fact that I will take that road. And I compare that against choosing a different strategy. What about if I go on S prime? And this is the notion of Nash equilibrium. But as I told you, they look very different. In one case, you have continuous variables. Here, you have random equilibria. So this I already mentioned, the case of Rosenthal, which is a potential game and have pure equilibria. But for heterogeneous, you only have mixed equilibria. Think of this case, for instance, very simple case. You have a single origin destination, so one type, and you have two routes which are identical. Let's say that I have to route 10 players. So there is obviously a pure equilibrium. Send 5 guys above, 5 below. Okay? But in fact, any permutation of the players is also an equilibrium. So you have a lot of pure equilibria. If you don't take into account the identities of the players, it's just a single one, 5 and 5. But you can also completely mix. Take every player and send with probability 1/2 up, 1/2 down. That's also an equilibrium. Or take 3 players, send them up, 3 players, send them down, and the rest mixed with 1/2, 1/2. That's another equilibrium. So there is a host, in fact, of Nash equilibria. And that's a problem for game theories, because if you want to predict, if I have 2,000 equilibria, which one will occur? In that sense, Wardrop equilibrium is much nicer. It has a unique solution. I'm simplifying a little bit, but under reasonable assumptions, strictly increasing cost, you have a unique equilibrium. It's much nicer. It gives you. But you see, in this case already, you observe some things that, if I send everyone up with probability 1/2 and down 1/2, the load on this link will be a binomial 10, 1/2. The expected value of that is 1/2 of the player up and 5 of the player down. And what is common to all these equilibria that I just mentioned is that in expected value, the load are the same up and down, split 1/2 and 1/2. And maybe you can conjecture that even if the weights are not exactly the same, maybe the equilibrium should look something like this, same 1/2 and 1/2. So here's the first theorem, which in fact is not very difficult to show, but let's see. Take a sequence of games, atomic, unsplittable games with weighted games, okay? And capital N denotes the number of the set of players. So suppose that the number of players explodes. You have more and more players. And suppose that the weight of every player is going to 0 uniformly. So the maximum weight of all players are going to 0. This is the natural setting where you expect to have convergence. You have many players, every player can become smaller and smaller. And then I suppose that there is a convergence of the total demand for every type. So I look at each particular type, I just count how much weight for that type is present in the nth game, and I assume that this has a limit when n goes to infinity. Then, take any sequence of mixed equilibria. It turns out that the expected strategy loads, so what you take is you sum for every t and for every s, you look at what is the expected weight that I would expect, that I would see on strategy S. It's just the weight of player I with probability pi I will observe it on strategy S. So that's the expected strategy loads. Well, it turns out that those are bounded, and every accumulation point is indeed a Wardrop equilibrium of the limit game for the non-atomic game. And moreover, if I take one such convergence subsequence, then those random resource loads, this binomial or whatever you get, may be very complicated sums of non-homogeneous Bernoullis. Well, those random variables converge in L2, therefore also in probability and in distribution. They converge to a constant. To what constant? The resource loads which correspond to the Wardrop equilibrium. And if the costs are strictly increasing, then we know that the Wardrop equilibrium has a unique resource loads, so that in fact, you get convergence of the full sequence, not only up to subsequence, but the full sequence converges to a Wardrop equilibrium. Good, reinsuring. Okay, that's what everybody expected, so it's not a big deal. except that it was not, we couldn't find it anywhere, this result. After 70 years of the model has been introduced, it's kind of strange, but if anyone has seen such a results, please let me know. Okay, that's very nice and very nice mathematical model, but you go on the road and what you observe is something quite different. So far we were modeling, our model was based on something like this. I have the load, the volume on the edge on the resource E, and I was claiming that my cost, C of E, was a very nice function like this. To each value of the congestion or the loads, it corresponds a precise value. But this is not at all the case, and we all know that if you go on the road at 8 a.m., probably sometimes you observe this value or that value. These are true data collected in Copenhagen. And you see, this is a long time of day, and let's say at 8 o'clock, what they did is that on consecutive days, they measure the travel time going from, I never see this, it's, I think it's this red segment here. They measure the travel time, and you observe different values. So you don't observe a wardrobe equilibrium. You observe random variables. So that was always something which was sort of, you know, it posed a lot of difficulties for me to match what wardrobe is saying, what is the meaning of those non-atomic equilibria. How does it connect with these random variables that persist, even if the congestion is high? So this led us to consider this model of atomic congestion game with random players. So players are now identical in terms of weight. All the players are homogeneous. They have exactly the same weight, but they have different probabilities of being present or active in the game. Okay, so I will denote yi, the random variable, Bernoulli, which tells me whether player I will be present or not. And this is a game with incomplete information, so you're playing, the question roughly stated is, how do you play a game where you don't know who are you playing against? Which is quite different from the standard notion of games. In games, usually the first assumption is let N be the set of players. And everybody knows that those are the players. Well, in fact, in this case, it's not. I don't know who will be the players tomorrow morning when we come to IMPA. Right? So let me denote now XIE will be the same meaning, except that now it has two random components. One is YI, whether player I is alive or not, and then the indicator whether player I is choosing a strategy that goes through link E. And then I denote VE, just the sum of the loads, as before, the number of players. Notice that now VE is a discrete variable. You know, these are, the XIE are 0 or 1. There are no weights involved. So we're no longer talking about real numbers, we are talking about integer numbers. These are random variables which take integer values. And as before, I say a strategy profile is a Bayes-Nash equilibrium if for every player and every strategist. If player I is choosing strategy S with positive probability, the expected value, this doesn't change. The definition is exactly the same. What changes is that now the expectation is taken with respect to yi and pi I. There are two sources of randomness. The randomization of the player, this is strategic randomization, and then an ex-ante randomness which determines whether player I is alive or not. Okay? Just a reminder, the costs now they only need to be defined for integer numbers. In fact, for n bigger than 1, because I'm conditioning on the fact that I'm only concerned with the source whether I am there. So the load will be for sure, me plus somebody else. So I only need the cost to be defined for integers bigger than 1, 1, 2, 3, and so on. Now it turns out that These are also potential games. There is a nice potential function. I will not spend too much time on that. Just believe me that this is a potential game, whatever it means. It has a nice potential function, and this means that it has pure Nash equilibria. But in what follows, I'm not only concerned with pure, it could be mixed or pure Nash equilibria. Now, in order to pass to the limit, I need some assumptions, and this is the main assumption. The standing assumption is that I will assume something about the costs. Roughly, I'm saying that the costs do not explode very fast. They should be such that when I take the expected value of x squared CE of 1 plus x with respect to a Poisson random variable, then this value is finite. I'm simplifying. It's a bit more general than that, but with this hypothesis, it's enough. Okay? So I'm considering this function CE tilde, so I'm lifting the original function, which are the CE, which are described only for integer numbers. Now I lift it to a continuous function, which is defined, this is called the CE tilde, which is defined for real x being the expected value of a certain Poisson random variable. Explicitly is given by this sum. Why is this 1 there? Because of just what I told you before. When I'm computing equilibrium, when I look at my expected cost for a resource, I count myself plus somebody else, plus the rest of the world. So this 1 will be myself, and this x will be the number of other players that are there, which I will show that eventually are Poisson variables. And I recall that the total variation distance for...
What is the assumption, really?
The assumption is this one. Is that this expected value is finite. This less than infinity, that's the assumption. In fact, I don't need for every Poisson, but for every Poisson with large enough x. That's the only assumption. So it is a very mild assumption. I forgot to mention that. This is true for all polynomials, every exponential or combinations of exponentials. You should avoid something like, the cost C, if it grows like factorial k or double exponentials, then those expected values explode to infinity, and you cannot get something which is not well defined. Okay? So this is the standing assumption, is that this expected value is finite. In fact, this condition, it tells you that this function C, which is defined as this power series, is in fact a C2 function. That's the x squared gives you a little more. If you forget the x squared, it will tell you that this is well defined. This is finite. I'm putting the x squared because I need a little more regularity. I need C2 regularity. But okay, that's just a technical assumption, and it holds for a wide class of costs. Now, just remind that the total variation distance for random variables, it's a measure of the distance between the laws of those random variables in a very strong convergence. So if you have this type of convergence, it tells you that, as a random variable, they look exactly the same. The probability of any event is close between x and y. They look exactly the same. So it's a very strong notion of convergence, much stronger than convergence in distribution or in probability. Much stronger than, in fact, it's called the strong convergence of random variables. Okay, so here's the theorem now. Suppose that I take a sequence of those games where players have weight 1 and have probabilities of being present, which are very small. And in the limit, I'm thinking of an increasing number of players, the presence probability go to 0 uniformly, and this is the expected load of type T, or the expected number of players that are present are just exactly the sum over all players of type T times the probability. This is the expected number of players of type T. And I'm assuming that in this sequence of games, everything is convergence. This convergence diverges to the infinity, the probabilities go to 0, and the demand stabilizes to a certain limit. Then, if I take any sequence of the Bayes-Nash equilibrium, I have again that the expected strategy loads are bounded, and every accumulation point is again a Wardrop equilibrium of which game? Of the game defined by this CE tilde that involve these Poisson variables. And in fact, along any convergence subsequence, the random resource loads, which before were in the WI going to 0, were converging to a constant. The variance was going to 0, let's say. They were degenerating to a Dirac mass. It is no longer the case. In this case, the resource load will converge in total variation, so very strong convergence, to a Poisson random variable whose expected value is the wardrobe equilibrium. So this is the way I want to interpret now. What is the wardrobe equilibrium in this setting? Is a characterization of the expected value of those loads, which will be Poisson. And of course, if the cos C, K are non-decreasing and non-constant, so it suffices to have one little jump. In that case, immediately the C tildes are strictly increasing, and therefore you have a unique wardrobe equilibrium in the limit game, and therefore the full sequence of resource loads converge to these Poisson variables. So let me call this the Poisson wardrobe model. Some comments. So first, weights going to 0 and probabilities going to 0, they both end up in a non-atomic limit game, but which have a very different nature. For vanishing weights, the random resource load converge to constant resource load. They degenerate. In the other case, they converge in total variation. The Poisson limit, moreover, is consistent with data which has been collected since the 60s. What they did, basically, you go on the road, you take a certain segment, and you count the number of cars that go through. And since the 60s, it is known that under low to medium congestion conditions, those variables, those counts, obey Poisson. So that's nice. At least there is consistency with that. If you go to higher level of congestion, the Poisson model breaks down because, you know, when the cars are bump to bump, okay, no Poisson regime is sustainable. But at least, you know, there is some consistency with true data and also with the Copenhagen noise that you were observing. And as I told you, for me, at least, the assumption that the probabilities are small, it's quite natural, because if I say I'm going out tomorrow at 8, what is the probability that you know, every other player will be present at the same time with me and competing for resources? That coincidence of probability, that probability is very small. So it's natural, in my view. It's more natural than thinking of a car shrinking to 0. It turns out that the Poisson limit that I just described is in fact a special case of something which was introduced by Meyerson for a different purpose of analyzing voting systems. And, but you can reinterpret this as a Poisson game in the sense of Meyerson. Maybe the interesting part is that Meyerson introduced Poisson games axiomatically, not as a limit of anything. So he said Poisson games are games with random populations, and if I want this and this axiom, then everything should be Poisson. In our case, it's a different matter. We obtain the Poisson as a limit of discrete games. And in fact, we can extend, and you can do the same for Meyerson Poisson games. You can also obtain, and we do that, we do obtain Poisson games as a limit of, and we're not talking anymore about congestion games, just general games. The connection between Poisson and wardrobe also were not observed as far as we know. So how much time remains?
10 minutes.
Huh?
10 minutes.
10 minutes, so that's enough. So in fact, now I go to the price of anarchy. Price of anarchy is a very popular measure of inefficiency in congestion games. It measures how much worse could be an equilibrium compared to the system optimum. Okay? So it's defined like this. You take C of pi is the expected social cost. What is the social cost? It's just the sum of all the cost experienced by every user. So you look at every edge, you look at the cost on every edge, you multiply by the number of people that experience that cost, you sum up. That's the social cost. And then you take expected value because, okay, everything is random here. And then you define C opt as the minimum of this expected social cost. What a central planner could achieve if he had the power to decide and enforce the decision of every player in the game. What is the minimal social cost? And we're going to compare this optimum reference value to what can be achieved through an equilibrium. What is the social cost of an equilibrium? And we have the choice of considering the worst equilibrium or the best. So the price of anarchy is when you consider the maximum cost among the equilibria and how they fare, they compare to the social optimum. And the price of stability is you just replace the maximum by the minimum. You consider the best equilibrium. Now, the first observation is that under the same conditions that we had for the congestion games, you have that the price of anarchy of the weighted and the game with random players, they converge to the corresponding price of anarchy in the limit games. Why is this interesting? Because computing this is really difficult. Computing this, there is a huge literature which has already done this job. Both, because in both cases we get to a wardrobe equilibrium. So you just go to the wardrobe equilibrium, compute the price of anarchy for the continuous model, and that's it. So for instance, if you have a game where the latencies, the cost of the links are linear or affine, we know that here you get 4/3, precise value, 4/3. So we know that in any random equilibrium, it will converge to 4/3. But now we're more interested not in the limit as p goes to 0, but can we describe what happens for any p? For large p, for small p, for p is always the probability. And the first thing you observe is that if you take a game with players which are random, the worst price of anarchy occurs when all the players are homogeneous. That's very common in extremal values, in extremal probability theory. Usually, the worst case among Poisson or mixed, what they call the binomial Poisson model, is obtained with binomials. So when all the players are homogeneous, that's the worst case. It is also here the case. So I will focus on what happens when all the players are homogeneous. And well, here's again the price of anarchy is, again, I take the price of anarchy, I take the worst case among all possible games within a given class. And I'm running out of time, so I will skip this. Maybe just focus here and here. It is known that for non-atomic games, the price of anarchy, and I forgot to mention, I will focus just on the affine case, affine cost and uniform players. We don't know for the moment how to go beyond that case. So it is known that with affine cost, the price of anarchy for the non-atomic game, the limit game, let's say, is 4/3. And in the other extreme, in the non-atomic case, with probability 1, let's say, every player is present, it's known that the price of anarchy is 5/2. So what we were expecting is that as we transition from p equal 1, we should go from 5/2 to p equals 0, we should reach 4/3. The limit, we already know from the previous result. We know that as p goes to 0, we should reach 4/3. And what we were expecting is a very nice smooth function of p. I will cut through. This is the analysis of how we get there. We use some techniques of smoothness framework to estimate this price of anarchy. That was the part on optimization, so I skipped it. And this is the bound you get. So we were wrong. It's not a smooth function. There are 3 regimes. When the probability is below 1/4, so there are 2 values, 2 critical values, 0.25, and then a very strange value, which unfortunately I do not have any interpretation of that value. It's just the solution of this polynomial equation, this cubic. And then what happens is that below 0.25, the price of anarchy is already 4/3. There is not an asymptotic, but you get to the asymptotic regime much earlier than p going to 0. Already if all the probabilities pi are below 0.25, your price of anarchy is 4/3. In the middle regime here, you get this very strange expression, 1 plus p plus square root of p 2 times divided by 1 minus p. You get that expression in this middle regime. This function is not convex, it's concave, in fact. And then you reach a third regime where you go back to convexity, and you get this increasing. So this is the profile of the price of anarchy. But this is an upper estimate. And in fact, it's an upper estimate not only for routing game, but for any congestion game. But are these bounds good or bad? Well, it turns out that, in fact, they are sharp. So we can get instances where these values of the price of anarchy can get as bad as these exact values. And the examples are, well, for large P, it's just this is a small network with 3 types, O1, O2, O3. I will not go into details, of course, but this network gives you this price of anarchy in the higher regime. This is a very simple network. It gives you, again, something which converges asymptotically to 4/3 when the number of links here is large. And the toughest was to find an example where the middle regime, because this is for the low regime, the previous was for the high regime. In the middle regime, it took us a while because we came up with this roundabout network, which is a sort of roundabout where, oops. Okay. So it's a complicated network, but in this case, you achieve this bound. So these bounds which we computed are in fact sharp. You cannot get better than that. So here's the summary. The price of anarchy is in fact equal to this bound. The worst price of anarchy is exactly equal to this bound. This is the function. And for the price of stability, we can combine with the previous recent result by Clear and Guido Schaeffer. It looks like this. This is the best Nash equilibrium. This is the worst Nash equilibrium. And again, this is also sharp. You cannot get below that. So in conclusion, we have convergence towards autonomic gain in the 2 regimes, weights and probabilities. We get convergence of the price of anarchy and price of stability. And there are several open questions, but I will leave that for the discussion, and I will end up by wishing you muy feliz cumpleaños, Alfredo.